Thank you. You've noticed that controls last, kind of like always. There's a there's a number of people that have been involved in this project, and I want to acknowledge this is not counting probably a great deal of people in ED who helped build the model. But one of the things I want to mention is that I was asked to talk about resilient, robust controls for distributed electric propulsion. 15 minutes is just enough to confuse everyone. So instead of talking details of controls, I'm going to try to lay out the problem that controls has and the opportunities. And if you have any questions about specifics, please come see me. I can spend hours talking about where we are now and what we can do. So challenges and opportunities. Well, multidisciplinary optimization. By the time you optimize the aero, the propulsion, the acoustics, you very rarely end up with simple dynamics that you have to control. So to use Nick's term, we take the ugly baby and make it into Miss USA. We still make it fly the way you want to make it fly. Another challenge is, frankly, model development. You know, the way we typically do we do vehicles, we take you to the wind tunnel, we do CFD. Well, lo and behold, just think of the number of test factors. Instead of having one propulsion effector or maybe two, you now have 18 to 22, and they all interact, and then you have surfaces. And so you have to go to the wind tunnel because CFD really, frankly, can't do it. And you have to establish some kind of database so you can control the aircraft. You can make it want to behave the way is desired, right? And also, it leads to increased level of automation that's leading to autonomy. Nick touched on this a little bit. We're not going to have a pilot who's going to control 18 throttles. There's automation that has to come into play. And so if this type of vehicle is to be widely adopted, you're going to have two things. One, it has to be affordable. And second, the skill of the operator will have to be reduced. It almost has to become like your car. So there's automation, and that will frankly lead to autonomy. Opportunities, well, increased safety. Distributed electric propulsion gives us a number of control effectors if something fails. So now if you have a single prop airplane, one engine fails, you are in trouble, and you have to glide to sort of hopefully the nearest landing zone that's safe. You have 18 of them, your one fails, minor adjustment, and it's not even an event. Chances are you have to have a lot more failures before you have to change the mission that you're performing, whether you're going you're 200 miles or you're doing something else, right? Another opportunity is the requirement for increased automation leading to autonomy. I mean, it frankly is both a challenge and an opportunity. And just as I said, just to point out, we're going from aircraft that looks like this to aircraft that looks something like this. So one of the things, though, was pointed out to me by my other discipline colleagues said, hey, you might want to talk about what kind of challenges multiple propellers present to the control system. So let me just give you a very quick overview. So we have a prop, and right now, this is not something new and different. This is something we deal with GA aircraft, but it's one, and it tends to be taken care of fairly easily. Well, now you're talking about 18 to 20. And so think of this as problem multiplying. So all of a sudden, we have all these extraneous things that controls has to take care of pretty much seamlessly, besides producing the performance, robustness, and everything else. These wonderful props induce yawing moments just because they rotate. There's asymmetric thrust that they all produce. If we're going to start getting these propellers tuned towards acoustics, then clearly we start talking about different rotating speeds, perhaps different frequencies. That all starts inducing different flow. That all starts inducing yawing moments. You also inducing rolling moments. They tend to be very tightly coupled. You also induce pitching moments. If you have variable pitch props, or you have props that fold because you don't need all 18 in flight, for instance, you start inducing all these extra things that typically we don't have to worry about. We do now with these type of aircraft. So back to actual distributed electric propulsion. One of the things I want to show you, just an example, I can sit there and wave hands about controls, how difficult all this is, but the best way to show the problem is to take an example, and we have a very good one. Mark alluded to it. We call it GL10. It's an aircraft that came out of particularly this type of mission requirement. So when a customer came to us and said, hey, this is what we want to do, we want a 24-hour endurance. Oh, and by the way, we also want a VTOL aircraft. Those two are very, very different type of requirements for the aircraft. We want low noise. We want to minimize tip over while we're on the ground, so no tail setters. We want to be able to land on some remote locations, so back to VTOL. And by the way, we don't want to pilot anywhere near this aircraft. We want it autonomous, both takeoff and landing, with no direct human presence. And there's some other requirements that was transportable in a small vehicle, which size the aircraft. And frankly, the mission applications for us is things like science sensor deployment to remote areas, atmospheric science measurements, package delivery, maybe PAVs. But it's a really nice opportunity to explore a lot of these technologies. So what does this aircraft look like full scale? It looks like something like this. Came out of the SAC-D, and they're wonderfully creative people. And it came up and said, hey, control this. Cool. So this was not the only configuration. There were a number of other configurations that were under consideration. A lot of them had the vertical takeoff and the regular cruise flight. But why did GL10? Why not something else? Well, frankly, redundancy of propulsion, so distributed electric propulsion, was the winner. It allows you to, as I said before, allows you to basically absorb failures of your propulsion. And if you're going to be operating somewhere in the field, things will fail. That's just sort of normal. And if you can continue your mission while it's failed, so much the better. We have excess control power in transition, and transition is a very big deal with these aircraft, and I'll allude to this in the next slide. We have potential for good stall performance because you can tailor the wing for your very long endurance, your loiter flight. That sort of requires good stall performance because loitering is you're flying right at the edge of stall. Engine out, recovery, and cruise, we're back to the fact that we have distributed electric propulsion. Even if we don't use all the props while we're in cruise, it's very easy to turn something on and do it quickly because it is electric. It doesn't take all that time to spool up. Wing control surfaces are in a prop stream, so that means that as my propellers are rotating, I actually have air that's flowing over my wing, even if I'm in a VTOL mode, which means my control surfaces are now effective where they wouldn't be otherwise. Let's see, there's mass distribution along the wing. There's a possibility of acoustic tuning. The small propellers actually give you also not only low rotational energy, but that makes them faster. So again, if something fails, the energy associated with the blade flying is a lot lower than if you have a single prop. Makes it less likely that you have a catastrophic damage to your structures. And as I said, it's something that potentially will allow us to do safe delivery of packages and anything else. So when we looked at this, the full-scale aircraft is about 22 feet. It's not something we typically develop and fly here, so we went and said, okay, well, let's do a 52% scale vehicle. That puts it into a small UAV class, or nearly so if we remove enough batteries. You go from 62 to about 55 pounds. You're talking about 124 inches wingspan, so that's what, 12 feet. The mission itself, as I said, there's three modes. There's the hover takeoff. So what's interesting about this vehicle, notice that both the wing and the tail have propellers. Both of them rotate in transition. And then when you finish transition, you basically look like a pretty conventional airplane. You turn off all the props except the two outboard ones. And you go on your long endurance loiter mission. And when you need to land, you turn all the props on, you rotate back, you vertically land, deliver the package, take off again, and do this as many times as your, frankly, as your batteries will allow at this time. So that's the mode of operations. One of the things I would also like to point out is, and hopefully that's seen, so before we do this, as I said, we have to do, typically we go to the wind tunnel. Well, that's great. This one has 10 propellers. It has 4 surfaces on each wing. It has a tail that rotates and 2 elevators on that tail. By the time you finish counting, You have 21 actuators. Oh yeah, and then there's the alpha and the beta. Do you have to vary in the wind tunnel? So that's 23 factors. If you go do that in a conventional way, the calculation takes you about 8 years. Not going to do it, right? So one of the things, there's two things that we had to do. One is we used the fact that there's some new capability we developed for wind tunnel where the rig could actually move automatically without somebody coming and resetting. And then we used design of experiments to make this, the test matrix much sparser. And what you see, and hopefully this video, is it playing?
Yep.
Oh, good. Maybe.
It's playing.
Okay. Oh, great. It's not playing on here. So what you see, this is sped up, I think, about 4 times. So this is actual testing. There's no preset alpha that you go alpha sweep or beta sweep. Everything is moving at once. And you're taking data in blocks. And this took us 40 hours to get a database that is good enough to do control or develop it. Now, if you're trying to get that last percentage out of your drag, this is not it. This is not going to give it to you. But if you're looking to actually do the testing in order to create a database that you can go and fly a new concept, this has certainly a great deal of promise and potential. What I want to show you here is once we have this database in, hopefully all of this is moving. Yeah. It is. So what you see on the left, this is directly from the simulation results of a hover transition and flight, and it'll go again. What you see in this data, this is going to be our altitude. Right here is stick and throttle. Here, as you see, wingtip angle. So as you can start seeing this red and the blue line coming down, that's we just finished going through transition, and we're going straight. Because this vehicle has so many degrees of freedom, there's so many ways of doing some of these controls type of trajectory and transition, and what do you use? And so that opens up a whole new question of design space. And in fact, sometimes there's too many things, and you have to decide what's the better one. So what it's really giving us, it gives us an opportunity to take the tools that we already have, that we applied on other projects very successfully in flight, and now develop these tools for configurations that are much different than what we have. However, since we developed these tools for something this unconventional with these many independent factors that we can vary, we're ready for almost anything else that's coming down the pike. Because at the end of the day, right, it's still F equals ma. You still have to produce moments or forces in order to control a vehicle. And so we think we now have our hands on a set of tools that allow us to do this a lot faster than before we started. Still not as fast as we would like, but certainly a lot faster, and that's some of the sort of next steps that we want to do. And so here's our next steps. So Mark has shown a video of hover that was done last week very successfully with a pilot in the loop. They will potentially continue to do that development through a pilot with transition and forward flight. For us, the next step is, frankly, autonomous flight. We're going to go directly from simulation, hopefully, to autonomous flight, so no pilot. Once this is complete, and assume that the controllers are as good as I think they are, the vehicle will come back in one piece, and it will become a research platform for advanced algorithms. Frankly, you can think of, if you're talking about modeling, I mean, welcome to how many factors, how much can we do in real time while we're in flight? Sensor development, autonomy-related algorithms. We have sense and avoid, navigation without GPS, vision-based guidance, a whole bunch of other things. And this is the one platform that we currently have that can stay in a fairly constrained space, and it's large enough that a small gust of wind is not going to, take it out 10 feet or 15 feet in a different direction like a quadrotor would right now. And it's also big enough to start housing some sensors that we probably have that, again, could be a little bit more advanced than what you can put on the small quadrotor. We're also continuing development of, as I said, a rapid prototyping. So the whole idea is, how can we do these configurations quickly? What if we don't take 2 years to do this? What if we can do it in 3 months. Oh, heck, what can we do if we can do from Sketchpad to flight data in 30 days? That's a goal we set for ourselves. It's very ambitious. Don't know if we're going to get there, but we're certainly going to be a lot faster than 2 years. And so some of the ways to get there is one, as I already said, automated tools. The other one is 3D printing. I mean, talk about rapid prototyping revolution. That's sort of that next step. And last but not least, it was asked of me, well, how do you get people to get involved? Well, frankly, propose. Propose through ideas or other advanced concepts, through the IRAD, through this NASA seedling, through the CAS, and come talk to us. We'll figure, you have good ideas, we'll figure out a way how to get it done. So, thank you.